Our solar system is a vast and diverse planetary system that contains 8 major planets, including one that has developed life. Humanity was born too late to witness the events that occurred during the formation of the solar system. However, by observing other star systems, we are beginning to piece together the events that lead to the creation of Earth and the solar system. With its dynamic climate, flora, fauna, and human inhabitants, our Earth is clearly a unique planet and rightfully called humanity's home. Yet for scientists, Earth and the other planets in the solar system are celestial bodies, adrift remnants of cosmic debris from the formation of the Sun, which itself is an average star in a very ordinary galaxy. Earth and the rest of the solar system were formed in a gigantic and dark period about 4.6 billion years ago. This process, driven by gravity, continues today in other parts of the universe, forming new stars and planets that obscure within layers of dust that absorb normal light wavelengths. To penetrate the heart of these cosmic constriction sites, astronomers use different wavelengths such as infrared or submillimeter waves. The aim of this research is straightforward. Observe a discerning regions where reactions and related to what likely happened during the formation of our solar system. Through this method, they hope to decode many mysteries. The first mystery is why the planets of the solar system orbit nearly in the same plane. Perhaps a natural process occurred preventing the planets from moving in random directions, and instead aligning them in intersecting orbits. The second mystery is the sudden change in the composition of planets from the center to the edge of the solar system. Some process separated raw materials to create the small rocky planets of the inner solar system, and the giant gas planets on the outer edges. To answer these questions, astronomers must identify and observe regions where stars and planets are forming somewhere in the galaxy. Stars and planets make up about 85% of the galaxy's atomic mass, with the remaining 15% belonging to interstellar regions where new stars and planets are born. This material floating through space forms a thin cloud of gas and dust, with hydrogen by the most abundant component. Dust includes particles of heavier elements produced by planetary nebulae and supernovae. A space there typically only about 100 hydrogen atoms per cubic meter compared to the Earth's sea level, where the air contains about 200 billion atoms. As hydrogen atoms in that galaxy tend to pair into molecules, these molecules clump together into giant molecular clouds. Astronomers estimate there are about 40 of these clouds in our galaxy, each with a diameter ranging from 150 to 250 light years, and containing enough gas to form 10 million sun-like stars. When these gas molecules accumulate, they cause the molecular cloud to spin. This phenomenon is critical for the formation of stars and planets. Within each giant molecular cloud, there are numerous denser clusters, each spanning about a quarter to a third of a light year in width. These clusters are the nurseries of stars, more precisely the initial stages of star formation. A cloud cluster generates gravitational force and starts to collapse in on itself in a long process, lasting from 1 million years. Shockwaves from nearby supernova explosions can accelerate this process by compressing the gas and triggering the formation of additional dense clusters. As a cloud cluster contracts, the gas and dust within it become more concentrated. Although dust only accounts for about 1% to 10% of a cloud cluster's mass, it's enough to block our observations of newly formed stars using standard light wavelengths. By peering into these dust cocoons with infrared telescopes, astronomers have witnessed amazing sights. Each collapsing gas cluster transforms from a nearly spherical shape into a disk surrounding a newly formed star. These solid disks can be 100 to 10 times larger, and the flattening of the planet-forming disk is due to centrifugal force, which is not an inherent property like electric charge, but arises when an object begins to rotate. As an object spins faster, the greater the centrifugal force it generates, pushing metal outwards, similar to a ball rolling outwards on a rotating carousel. Now consider the gas and dust cloud that formed our solar system. As a spherical cloud collapsed under its own gravity, it naturally spun faster, much like a figure speeds a hyperspin by pulling in their arms. This concentrated the centrifugal force on the cloud's equatorial plane, opposing the gravitational pull in the gas and thus slowing down the collapse in this area more than elsewhere. The influence of centrifugal force is significant. Gas and dust drawn inwards have more freedom to move, eventually flattening the cloud into a disk. Within this flat disk, matter gradually coalesced into planets, and therefore the planets lie on nearly identical orbital planes instead of moving randomly around the sun. This explains the first mystery. The second mystery, the drastic difference in the composition of planets from the inner to the outer solar system, is due to the Sun. When the Sun was newly formed, reached its kite size and density, and began releasing energy, the heat prevented certain chemicals from forming by pushing their atoms into erratic motion. Atoms and molecules less affected by temperature collided and bonded with each other, creating a layer of dust and various chemical compounds. The chemicals formed depending on the temperature, which depended on the distance from the forming Sun. Near the Sun, where Mary's orbit, would eventually be temperatures reach several thousand degrees. Almy metallisms and silicate compounds could condense and decost. This is why Mercury's metallic core is proportionally large compared to its volume. Other chemicals could evaporate back into gas under the heat of the young Sun. Some like cooler near Earth's eventual orbit, silicates could condense more abundantly, making Earth's metallic core smaller relative to the planet. Farther earthward, temperatures with lower, different elements could condense into dust in the planet-forming disk. The distinct boundary emerged about 5 times farther from the Sun than Earth, known as the snow line, marking Jupiter's orbit today. At the snow line, planetary matter condensed temperatures were about 90 degrees Celsius, low enough for molecules like water, ammonia, and methane to freeze. In regions about 40 times farther from the Sun than Earth, near Pluto's orbit, temperatures dropped to about 220 degrees Celsius, and most chemical elements could condense except for hydrogen and helium, which remain gaseous. As a result, the dust particles formed different compounds across the planet-forming disk, leading to the diversity of planets. The fact that the outer planets are significantly larger could be explained by the abundance of material beyond the snow line in the outer solar system. The dust gradually accumulating to asteroid-like bodies, these protoplanets once dominated the early solar system in vast numbers, necessary to form Mercury, Venus, Earth, and Mars. It would take about 10 billion protoplanets, each about 10 kilometers in diameter or more. These rocky bodies continued to grow primarily through collisions and accretion. At first glance, this process seems straightforward, but it's more intricate. Direct collisions are inefficient because they release too much energy and could shatter the protoplanet, scattering fragments into space. Instead, close encounters where one protoplanet slightly nudges another could lead to mergers. As these both headed in the same direction, sometimes a nudge was enough to cause them to melt together. Even if they shattered, the fragments remained bound by gravity, continuing to orbit as a clump of debris. These near-collision events continued randomly until a few larger protoplanets developed enough gravitational force to attract smaller ones towards them. Throughout the planet-forming disk, these larger protoplanets began to outpace their smaller counterparts, outdrawing in small bodies. Astronomers call these protoplanet oligarchs because they dominate their surrounding space. Essentially, they are rocky planets larger than the Moon but smaller than Mars. Computer simulations suggest that 20 to 30 of these oligarchs eventually collided to form the 4 terrestrial planets we see in the solar system today. The giant gas planets in the solar system, Jupiter, Saturn, Uranus, and Neptune, likely formed in a similar way as the thinner planets, but from larger oligarchs augmented by cosmic ice. When Jupiter and Saturn reached a mass 3 to 5 times that of Earth, they developed enough gravitational force to start pulling gas from their surroundings, forming extensive and rich atmospheres composed of various chemical elements. Uranus and Neptune formed similarly, but being smaller element attract as much hydrogen and helium, resulting in a higher proportion of cosmic ice in their atmospheres. Some astronomers propose that the giant gas planets formed like stars. According to this hypothesis, the region around the Sun reached significant density, and gravity pulled the gas inwards, leading to the sudden collapse of gas into a giant planet. Today, there is no way to definitively determine which scenario actually formed the gas planets in the solar system. Both theories accurately predict that each giant planet would have a smaller disk around it which later coalesced into a satellite system. In the distant region containing Pluto, the material orbiting the young Sun was thinner, so the celestial bodies formed a little smaller. Pluto itself is only 2/3 the size of Earth's moon and has a significantly inclined orbital plane compared to the other planets. In 2006, these factors combined with the discovery of similar celestial bodies at the solar system's edge led the International Astronomical Union to downgrade Pluto from a planet to a dwarf planet. These newly observed bodies include Home and Majestic. But it was the classification of 2313 that really sparked debate. Observations showed it was at least as large as Pluto, if not larger. Thus, astronomers faced a choice: downgrade Pluto or declare 2313 as the 10th planet in the solar system. A heated debate ensued to 2313 later, named Aries after the Greek goddess of discord as strife fitting for its role in the controversy what deemed a planet in Pluto was demented. There are really many more undiscovered dwarf planets in our solar system. Astronomers estimate that beyond Pluto there could be hundreds, even thousands of dwarf planets, and a few of them could be complete planets. Indeed, computer simulations suggest it a second solar system with numerous planets might be lurking somewhere thousands of times farther from the Sun than Earth. These could be as large as Mars or Earth, and though not originally formed, they could have been swept into these distant orbits by the gravitational pull of the giant gas planets. If these planets move fast enough, near a giant gas planet, its gravitational pull is not strong enough to pull them into a collision. Instead, these smaller bodies gain significant speed in a near miss and are pushed into larger orbits. In this way, Jupiter might have flung rocky planets far from the Sun 25 to 250 times farther than Pluto until it's so distant that they become extremely dark and difficult to detect. Moreover, Jupiter might have pushed them into any orbital plane, so the only way astronomers can find them is by scouring the sky with powerful telescopes. Nowadays, many such tools are being developed for this purpose. About 4.6 billion years ago, the solar system was much like it is today, with the familiar planets and their moons already formed. However, the space between the planets was home to numerous smaller celestial bodies left over from the formation process. These small objects, ranging from pebbles to protoplanets, escaped the gravitational pull of the planets and varied greatly in size. Jupiter's gravity trapped many such objects between and Mars, forming a main asteroid belt that orbits in the solar system. For the next 700 million years, these cosmic wanderers collided with planets and moons, creating craters of all sizes. Today, the cratered surfaces of planets and our moon stand as evidence of this intense bombardment period. Or if most of the ancient craters had disappeared over time, with only about 200 known today, all from relatively recent impacts. Earth's position inside the snow line indicates that there was no water on the planet when it first formed. The heat of the young Sun would have evaporated any newly formed water molecules. One major question astronomers seek to answer is how oceans came to be. The answer may lie in the final phase of bombardment, where protoplanets formed in the outer solar system containing water, and cosmic ice crashed into Earth, and the inner planets bringing water and other volatiles that are left. On Earth, these substances quickly transformed into life. During the bombardment phase, many fragments of protoplanets were flung out of the intersolar system after grazing past Jupiter. This process formed the irregular moons orbiting Jupiter, as they are much smaller than the planets. Jupiter could have flung these rocky bodies far from the Sun, 25 to 250 times farther than Pluto, into orbits so vast that they form a huge population called the cold cloud. Sometimes a few of these objects return to the inner solar system, and we call these visitors comets. Composed of ice, they gradually melt as they approach the Sun, trailing a string of gas in space that shines as a comet's tail. The dust emitted from the melting ice flows into the space between planets, and if it enters its atmosphere, it blends up, creating meteor showers or shooting stars. Sometimes, if a dust clump is large enough, It doesn't completely burn up when it rapidly descends to Earth as a meteorite. Fragments from asteroids can also fall as meteorites. About 700 million years after the heavy bombardment period, the formation process of Earth and the rest of the solar system was completed as we see it today. But until now, our understanding of the most recent bombardment event remains limited. In 1993, fragments of comet Shoemaker-Levy 9 continuously struck Jupiter. 21 fragments, some as wide as 2 kilometers, relentlessly hit the giant planet over 6 days. Each impact at speeds of about 60 kilometers per second caused massive explosions, creating numerous fragments, some even larger than Earth, visible in Jupiter's atmosphere for weeks after. Spacecraft in orbit have shown that many house-sized comets regularly approach Earth, but fortunately they disintegrate in the atmosphere and cause no threat. However, occasionally a large celestial body makes a significant impact on Earth. The most notable event was in the Tunguska region of Siberia in 1908, which obliterated a forest area equivalent to a major city like London. Asteroids that pose a threat to Earth were continuously monitored. Although most asteroids remain safely within the main belt between Mars and Jupiter, an increasing number of near-Earth objects are being discovered. Astronomers are tracking about 20 near-Earth objects larger than 1 kilometer in diameter. Currently, these objects pose no threat to Earth, but calculations indicate that on average an unravel size impacts Earth every 500,000 years. There are also thousands of small asteroids near Earth, with only a small percentage being monitored. One such asteroid, designated 2007 184, about 130 meters in diameter, has been identified as a minor threat. Although small compared to other asteroids, if it were to collide with Earth, it could release energy equivalent to 100 atomic bombs like those dropped on Hiroshima. The probability of it impacting Earth in the next 50 years is 1 in 30. But this is expected to decrease to 0 as more precise observations allow astronomers to better determine its orbit. More advanced devices are being continuously developed to detect and track near-Earth objects. One day, scientists are likely to discover an asteroid in a collision course with Earth. When such a prediction is made with relative accuracy, ready plans will be implemented to alter its course. Astronomers have devised numerous methods for this purpose. Shattering an asteroid into pieces with nuclear weapons is not a good strategy, as it would not change the trajectory of the fragments, turning a bullet into a shotgun blast. However, detonating a nuclear explosion on the surface of an asteroid could be a more viable option. A few layers of rock would melt, releasing gas to create a natural rocket engine to nudge the asteroid onto a safer orbit. It is ironic that the very celestial bodies that once brought water above, helping to spark life, now pose a threat to destroy it. In terms of protecting Earth from these threats, we can only wait for new developments to be updated. In the case of the asteroid 2007 184, even though its potential impact is small, it is a reminder of the constant vigilance required to safeguard our planet. The ongoing search and monitoring efforts by astronomers are crucial in this endeavor, ensuring that any potential threats are identified and addressed in time. The detection of Earth from celestial hazards is a complex and ever-evolving field requiring continuous observation and research. Preparedness.